Okay, so now we're going to go through exactly how Hopfield's model works and the technical details. So what we have here, we have two inputs. I'm going to use colors. Okay, so we got two inputs here. And to train our model, what we do is, so we take this number, we convert it, and so ones stay the same and zeros become -1. What Hopfield uses in his paper is this equation, 2b minus 1. And so because we're only allowed to have ones and zeros as our initial inputs, on or off, if you do 2 times 1, you get 2 minus 1 is 1. If you have 0, then 2 minus 0 cancels, it's nothing. Minus 1, so you get -1 or 1. That's what he uses. I think it's easier just to say 1 becomes 1 and 0 becomes -1. Whatever, to each his own. Anyhow, so what you do first of all, you take the inputs you're going to train the model on, and you basically make a matrix out of it. So what you could imagine, do this in green. So you have basically a 1, 1, minus 1, 1, 1, 1, minus 1, 1. And you multiply them out like a multiplication table. And you produce this matrix. Once you have that, then you go into the next entry and you make its matrix. You add the two matrices together, which is just typical matrix addition, and you produce this train matrix. And you're not quite done, but you're getting close. And once you have this, then what Hopfield mentions is, okay, what these are representing is basically connections between the neurons, between the entries. And something connected to itself doesn't make much sense mathematically, or in most cases in life. And so he says, these are cases where you have the same thing connected to itself, one connected to one. Anyhow, because they're self-connected, it doesn't make sense, so you have to just remove them. That's what you do. You cross out the self-connected entries, and you have this matrix. And so this, finally, is your trained matrix. And so I will write that out. Trained matrix. Okay, so this is your trained matrix. And once you have your trained matrix, what you do is you just expand it so you have room to enter values here. And so what we're going to do here is we're going to enter 1, 1, -1, -1. See, these are ones here, -1s, -1s. And so what this is equivalent to is if we entered 1, 1, 0, 0 into our trained matrix. And so if you look at this and you compare this to the entries, it should be clear that it's much more likely that this, what's intended is option A. I can, I guess, label these A and B. So what's intended here is option A. But one of the ones got messed up, became a 0. But what Hopfield was so excited about with this model, or I should say this was in 1982, was that the model is robust to these kinds of malformations. So you can just put in a partial input or a mistaken input, and you will in fact get the full answer. So plug it in. So first you always have to convert these into ones and -1s to enter anything. Once in the model, it may not. You may have zeros. You may have +2 and -2 and things like that. But entries have to always be 1 or -1. That's required. So this becomes 1 +1 +1 -1 -1. Then you enter that into the model. So you multiply these values together. So you're essentially multiplying this vector by this matrix, and then you add those up according to the columns. So add this column, this column, this column, and so that's what we did here. 0 times 1, 0, 0 times 1, etc. Negative 2 times negative 1 is 2, negative 1 times 1 is negative 1. And so we get these different outputs, 1, 0, 0, 3. So then Hopfield explains that the way you get this into your final form is if the value, I'm going to have to erase something, so just a second. I'm going to have to erase this. It's not very important, but if you like it, great. So Hopfield, the rule Hopfield had is if these entries, call them, his terminology was V, I think. I'm going to check his terminology just a sec. Okay, his terminology for this was V. So, okay, V it is. So if V is greater than 0 equals plus 1, V is less than 0 equals negative 1, and V equals, that didn't turn out right. And if, I'll do it on here, V equals 0, then keep the value of the input. So in other words, if V equals 0, if one of these equals 0, then just keep the value you had in the input, which was, this is our input. Same thing as this, different form. So here we go. So we have our different outputs for when we, this is during, the term inference. And so you have 1, 1, and 1, 0, 0, 3. And so 1 means, well, that stays 1. I shouldn't say that stays 1. That's not proper terminology. It is 1. And because it's 1, it's greater than 0, so it's 1. So we got a 1 here. And 0, that means keep the value of the input, which is a 1. And then this 0 means keep the value of the input, which is a 0 here. And then 3, well, that is greater than 0, so it's a 1. And voila. Almost as if by magic, we have our value A. And this is the big deal with the Hopfield network. Through this model, we are able to retrieve values, even if we're searching for them in a way that's kind of butchered, we can still get the correct output. So you could imagine the use for this in cases like you have a database of articles and you have titles to articles. Like, he gave an example, like Venier published a paper in 1948 called, I don't know, let's just say frogs. And so even if the user forgot a little bit of the name, and they said it was Bomber Frogs 1948, this would still most likely be able to correctly rectify the input and then do whatever you want with it. Plug it into a database, find the article, whatever. So this is really cool because it just helps fix butchered data entries or just incomplete data entries. Because zeros could mean just incomplete data. Anyhow, pretty cool stuff. Now, there's some limitations to this, of course, like everything, and that's what I'm going to show you next. So, okay. Limitations. One of the limitations is there's only so much you can store in one of these matrices of, he called them content addressable memory. So you have your matrix, I'm just filling out random numbers, but anyhow, this is our matrix. I made a mistake here. It's not ones and zeros, it's ones and negative ones. So 1, negative 1, negative 1, 1, negative 1, 1, 1, negative 1, oops. 1, negative 1, negative 1, 1, and then 1, 1, 1, 1. Anyhow, so he had this value n, and what n is equal to in this case is n equals 16. So he said that he figured this out by Monte Carlo calculations, that you can only store 0.15 n unique memories. So what that means is 16 times 1.15 equals, okay, let's run the math here. So 8, then we got 16, so we have 2.4 possible entries. So 2.4 possible memories. What this means is, of course, you can't have a fractional memory or a decimal memory. It has to be 2 or 3, or 4 or 5, whatever. And so he said the problem you have if you have more than 2 memories in this case is you get severe forgetfulness. So you might have forgetfulness with lower numbers of entries, but in this case you get severe forgetfulness. So a way to imagine this is if you're making tons of these matrices and you're adding matrices on top of each other, you can have things like you have 1, and then in one matrix, and then you have -1 in your other matrix, and it cancels it's out. Or you're adding 5 matrices together, and 3 of them have 1 in this place, and others have, and another one has 0. But which one has which? It's undecidable. And so as a result, the model will essentially forget older memories. It's just, it'll only remember the 2 most recent memories. It'll have traces of the other memories, but it's not going to be clear enough. And that's the major problem with this model. But that's not really a problem well, it's a problem with the model, but also it's a problem with just memory in general. Humans forget things too. If you overload your memory, you forget things. If I say too much in too short of a time, you're probably not going to remember it all. Like, if you recite like an equation once every hour, probably going to remember it better than if you recited it like, I don't know, 6 times in 6 minutes and then just didn't do it the rest of the day. Anyhow, so this is the Hopfield model, and it allows for implicit memory storage. You're not going to look at this and say, okay, this is a tree, or this is whatever. You just kind of, that's the whole thing with connectionist AI, which is the big thing now. And that's all there is to it. you can actually read the paper itself, and he'll use his own notation, which is not nearly as easy to read as this stuff, but this is what he's saying essentially. And so that's it for tonight. I hope you enjoyed. Please like and subscribe, and see you in the next video. And if you haven't watched it yet, watch my Perceptron video, and it will explain to you more things about what is connectionist AI and things like that.